Hello everyone and welcome back to another pattern recognition lecture video on deep learning. This video is a direct continuation of the previous video on convolutional neural networks. Now we'll be looking at popular CNN architectures all the way back from the 1990s and up until today. The first convolutional network we'll be looking at is lenet, and the first version of this network was introduced in 1989. And the latest version, lenet 5, from 1998. So this network here was used to automatically classify handwritten digits on bank checks in the US. And one of the main ideas behind this work was to use convolution for local precipitous fields and weight sharing. So exactly what we know about convolutional neural networks today. Then there were some minor details here. Namely that the output was a Gaussian RBF kernel, or there was such a kernel just before the output layer. So this you will not see much of today. And also the pooling layers, they used average pooling for the subsampling. But besides that, then we had the input. There is convolutions, and we can see here the two different versions. So in top here, is lenet 1 and in the lower lenet 5, and they still have more or less the same architectural design. So at first there was some kind of feature maps, afterwards some subsampling, more feature maps, subsampling and feature maps, and then there were some fully connected layers here in the output. And a thing also to note is within the network, the activation functions you put in was sigmoid functions, whereas today you'll more rely on ReLU to that. Well, both sigmoid and tanh function in fact. And the total number of parameters in this network here was just 60,000 parameters, which for back then was quite a lot of parameters. But nowadays you'll see networks with even 100 millions of parameters. And this network here, it was not, as you see today, optimized for GPU implementation. It was simply running on the CPU. Then in 2012, we have AlexNet, which is what started the current interest in deep learning by performing very well on this newly released, at the time at least, ImageNet dataset. So there were quite some details in AlexNet that were different from lenet, but beside these small details, then a lot of it was just the same structure, in fact, as lenet, which dates all the back to the 80s, as you saw. So one thing was to use max pooling instead of average pooling. Then the activation functions are switched out, so now we're using ReLU instead of tanh activation functions. Then on the input for the images, in the paper, they're using a lot of data augmentation to prevent overfitting, such as mirroring, random crops, intensity change, and so on. And they also introduced dropout to avoid overfitting on the data. Some details here to note is that the implementation or the network itself, it took up so much storage, so much memory, that it couldn't fit the network onto one GPU at the time. So 2 GPUs was in fact needed. So a lot of the details in the paper from back then, from 2012, was in fact on this dual path way, how this was constructed and what each of these two graphic cards then were responsible for learning. And in total, over the 2 GPUs, this network has around 60 million parameters. If you look up the AlexNet implementation for today, then you will not find this dual path implementation of AlexNet, but instead you'll find an implementation which fits perfectly fine on a single GPU of today's standard at least. So here is just a bit easier sketch than the previous one you saw from this website Learn OpenCV, where they also show that just like lenet, this AlexNet also just consists of convolution, pooling, pooling again. Here is both the pooling and convolutions, convolution again, and so on. And then in the end, we have this fully connected layers. So a lot of the structure is the same, but one thing that you might question a bit here is, okay, how do you figure out that here should be exactly 11 times 11 convolutions and stride 4? And why do we do pooling here of 3 by 3? And then the next part, convolution here is 5 times 5 instead of 11 times 11. And the padding is now 2. So all of these different parameters that you can change, like why were these decisions made? So instead of AlexNet, where we had all of these parameters to tune, then in VGGNet, which stands for Visual Geometry Group, which is a group at University of Oxford, they had this idea to simplify the convolutional layers in a neural network in some kind of repetitive format. So what they came up with was to only use 3 by 3 filters with stride 1, same convolutions, then have max pooling only of 2 times 2 with stride 2. Then layer size, if layer size goes down, so after max pooling, then the number of feature maps, they go up equally. And with this VGG network, they published a lot of different flavors of VGG with different number of parameters. So we can see one of the smaller ones, VGG 11, had, so 11 here just refers to how many layers in the neural network it has. And number of parameters here were 133 million parameters. And then we can see that the more layers as such we add, so VGG 11, then there was VGG 11 with some kind of local response normalization. So they added a normalization here in the beginning, which, as you can see on the arrow at least, did not do make any change as such. Then VGG 13, add 2 more hidden layers. Again, increases performance and number of parameters is still around the same. Then we can increase the depth again all the way up to the VGG 19, where it seemed like the network structure, this kind of network structure, seemed to be worsening again a bit. So going from 8.8 error with VGG 16 to 9.0 error on this top 5 error on ImageNet using the VGG 16. An alternative approach to VGGNet, so also as an extension to AlexNet, was lenet. It is called informally, or in the paper it was called InceptionNet, also from 2014. And there, instead of saying that we only do this one type of convolution and then pooling, then what we want to do is do all kind of different kind of convolutions and pooling at the same time, and have this in some symbol structure and repeat this structure throughout the network. So again, see this as an extension to AlexNet, where it was all kind of different convolutions that were used. The pooling strategy was not that consistent, so they really tried to come up with some simple rules here. And instead of VGG, where everything was straightforward, like only do one kind of convolution and then downsampling, then here we will do a lot of different kind of convolutions. So the idea is to have some way in the network we'll have this image volume, where in this case now the image is all the way down to 28 times 28, and then we have these 192 feature maps. And then we'll do what we'll do with this image or this volume here is to perform both 1x1 convolutions, 3x3 convolutions, 5x5 convolutions, and max pooling and just stack all of these outputs together as the next volume in our network. So very naively, this would look like this here. Like if we have a 28 times 28 times 192, and we want to have some convolutions such that we end up with 28 times 28 times 32. What this would mean is that we would end up having 120 million parameters just for all the parameters between these two hidden layers. This here is the naive version of their what is known as the inception module, like this block that they repeat throughout the network. So they also introduce that you have to do some tricks to actually make this work with some feasible amount of parameters. So they go ahead and add some 1x1 convolutions before both these 3x3 and 5x5 convolutions to avoid having the number of parameters totally blow up. So if we look at the numbers here, if we go back from 28 times 28 times 192, and then we do 1x1 convolution to reduce the feature maps down to 16, and then afterward we can do this 5x5 convolutions of this volume with a reduced feature map. Then we end up with, in the first convolution, the 1x1 convolution, we end up with 2.4 million parameters, and in the second one we end up with 10 million parameters. So this here would be just 10% of the parameters as needed as what they refer to as the naive version of this inception model. Here we then have an overview of the full network with a lot of these inception modules all over. We also see that beside having these inception models, then they also have some side branches going out here, and then we have the output of the network up here. And these side branches, they're just used as intermediate layers to do also prediction and to help to compute the total cost. So then you would also be able to backpropagate from these side branches here and avoid some kind of vanishing gradient. A very interesting thing about this paper was that in the original paper, they in fact had a citation to a meme from the internet about which refers to the movie called Inception. This is one of the very few times I've seen such a citation in a scientific paper. And maybe also note to the nickname lenet, which is a nice tribute to the original lenet back from the 80s, as we saw as the first convolutional neural network in this video here. Yet another convolutional neural network architecture was introduced in 2015 in the paper Deep Residual Learning for Image Recognition, and the network here, or the architecture, is what is often referred to as ResNet. And the idea here is to use skip connections to forward the output from activations to future layer inputs. And this allows to train really deep networks as it avoids the vanishing gradients. And the reason why it avoids this vanishing gradient is that the gradient can travel back through this skip connection. And also, as such, the skip connection doesn't hurt, as it is easy to learn the identity function. So we might end up that f of x here learns the identity function, and as such, we're just forwarding the input from the previous layers. Then we'll just have a layer in our neural network that doesn't do anything, which is better than it doesn't, like we cannot learn the gradient in that layer to continue to backpropagate further in our network. So here is just a formulation that a skip is added before the second activation function. So we have an activation function here and also in here. So an input is put in through some convolutions, then an activation function, then some convolutions more. And then we add the input from a few layers back before running it through the second activation function. Here on the right side, we just have an example of how a 34-layer plane and also residual network looks like, where we see in the residual version, there's just the skip connections all the way through. And we also see that the network here follows partially the same trick as in the VGG to double the feature maps when we perform pooling. So we start out with a feature map of 64, and then after pooling, then we have feature maps of 128, 256, and then 512 in the later layers in this deep neural network. And there exists a ResNet version with 152 layers, and this network has just 60 million parameters. On this slide here, we just have some numbers for ResNet, where we see that it outperforms both VGG and also InceptionNet, especially with this 152 layer network, where the top 5 error drops all the way to 4.49. Just as an extension to the ResNet network, then in 2018 there was a paper where they are trying to visualize the loss landscape of neural networks. And in that paper, you'll find this visualization here, where they came up with a method to, in some easy way or some explainable way, visualize the loss landscape of neural networks, where we have a loss landscape looking something like the one to the left if we are not using any skip connections, and the one to the right way smoother if we are using skip connections. So these two networks here, they just looked at the loss landscape difference if using a ResNet 56 with or without skip connections. Instead of trying to come up with the perfect architecture manually, there's also a whole area of research focusing on neural architecture search, short NAS, where the idea is to have some system that automatically tries to come up with a good architecture for you. So you can see it in such a loop here that we generate some hyperparameters. We'll look at those in the next slide. Then we train a small network using these parameters, maybe on a small data set, it's a CFAR. Then we're able to compute the gradient of these hyperparameters, feed those back to a controller, which can then update our architecture. And then we can train this new architecture on the same data set, and then over time we'll convert to what a good architecture is for a certain application. So here is just some of the parameters that the network is used to search on. So in the filter height, width, the stride width, the number of filters, layers, number of repeats, the skip connection, and so on. So the idea here is to split the computation across multiple machines with a central server, parameter server, and then the central server would then send out what parameters for a network should you use. Then it will train a neural network and then feed back the result to this central parameter server. In the paper here from 2017, they had a controller which trained in total 12,800 architectures. And after that, then it figured out what a good architecture looks like, and then it trained a lot of the found architectures onto the convergence. So it just trains a bit, just a few epochs, sees if it looks promising, and then compute gradients on that, update the network architecture, and loops over again. So this here is definitely not something that everyone can do. So in the paper here, they used 800 networks being trained on 800 GPUs concurrently at any time, with a total running time of 28 days. And this here is just like if you have both resources and also a large data set enough, then you can really try to figure out what the most optimal architecture might be. But if we look at the overview of how good these neural architecture search then performs, then we see that it in fact here, even the best one, version 3 with max pooling and some more filters, it in fact does not, it's just comparable to this DenseNet here from 2016. So it just gets a comparable result. So far we have only focused on neural networks which takes a simple input image and then puts out a vector where there is a probability for each category that we're training on. And all the networks so far, they've just been training on, well, both the small CIFAR dataset, but mainly on ImageNet dataset, where we had these 1,000 different classes to train upon. So UNet here does something different. So it's an architecture for image segmentation, and this this kind of segmentation or this network here is really good, especially within medical images. And this especially as it works with very little data and is trainable end to end. And the network is set up in such a way that, well, it looks like a U from where it has its name. So this U structure here. And at first, to the left, it has this encoder here. And then afterward, it has the decoder over here. So the idea is that in a downward path from the input and then all the way down to our latent variables down here, then we increase what is in the image, and then we reduce where this is located. And then again in the expansion, we create a high resolution map for where this actually is to be found in the image. And then we end out with a dense segmentation. So what UNet in fact does is give a single probability estimate, so classifying each individual pixels to belonging to a group or not. So using binary cross entropy to classify each pixels, so you get a value between 0 and 1 for each single pixel in the input. So an example here, the input and the output, they are of different dimensions. So to segment the full input image as we have here, you will just have to pass smaller segments into the network and then stack your outputs together. So we have all of these networks that have been trained for hours on, for instance, ImageNet, and it might not be everyone that has the resources to do all of this training again, or the time to wait for this. Or maybe you have a way smaller data set which is not at all big enough to train 60 million parameters on. So an alternative trick you can make use of is, let's say that we have this network. It does not matter what kind of network it is. Let's just say it's AlexNet. It's trained on ImageNet. And on the output here, we have the classification layer. And in between, a lot of convolutional layers and maybe some fully connected layers. And then you come with your own data set. Let's just say you have an image data set of cactuses. And now instead of, so maybe you don't have millions of images of cactuses, but you just want the output to classify between 4 different cactuses. So instead of retraining every single layer, then you might remember that some of the earlier layers in a neural network, they are learning very simple features, such as edges and some color changes and so on. And just in the later layers, we're actually combining this into objects. So what we can do is freeze most of the layers in this network, replace just the classification layer, the output layer, and on using our own data set, then we're training the network, but we're only updating the weights in this last layer. If it doesn't perform too well, we can even go ahead and unfreeze our maybe 2 last layers and just train the parameters in the 2 last layers. So thus there is no fixed number of layers that you have to retrain. The more data you have, the more of the layers you might want to retrain, especially of the later layers. But this here is a very simple way that you can make use of a lot of pre-trained models that exist out there on your own small data set. So we have these huge, deep neural networks with millions and millions of parameters. And what the intuition is that they are able to achieve some kind of high generalization performance. But now it turns out there is some problem still with these networks. And this is what is known as adversarial attacks, which in fact has turned into a whole area of research by itself. Like, how can you try to fool these convolutional neural networks into believing it's something else? So let's say here on the left we have some images which the network classifies correctly. For instance, a dog here, a speaker. Then we add just a tiny amount of noise to these images. So to the human eye, these images, even though they might seem slightly noisy now, they still look exactly like the same object. But what the network now is classifying is that it's classifying each of these images as an ostrich, which is definitely not the case. We can also look at just random noise. For instance, the image here on the top left, where this random noise is classified as a centipede or a peacock. And we have these 2 other random images which are classified as a king penguin or a starfish. And this here is with classification confidence over 99%. So it's not just that it's saying, oh, with a few percent, I'm a few percent certain that this is, for instance, a starfish. No, the network is really, really certain about its output here. And as such, you might not see this that big a problem if you add some random noise to the network, that it outputs something random. But where this becomes really problematic is, for instance, let's say you have a stop sign here, and then you add these few stickers to it, and suddenly the neural network does not see this as a stop sign, but instead of it as a speed limit sign, speed limit 45 sign. So obviously this here is a huge security risk for deep neural network systems, especially for self-driving cars. If it cannot detect a stop sign or a pedestrian, for instance, and one does not even need to know, well, in fact, one does not even need to know the deep neural network and its weights. You can simply, if you have a system where you can just send images and get the response, what do I see in this image, then if you just send enough images or slightly manipulate the image enough times, then in fact you can infer the full model and all its parameters just by having this mechanism by sending images to the network. So with this example here, it just says something about that even though we can do a lot of stuff with deep learning systems, then in fact they do still not understand the world. So they do not obtain some kind of intermediate representation of how a dog looks like or how a cat looks like. Because if we can change just the pixels slightly, then suddenly it does not classify this as a cat or a dog anymore, but as something totally different. So far we have more or less only been talking about image classification. So in the case where we put into our system a single image, so we have an image here, then we feed it into our deep neural network, and on the output we have some kind of fully connected layer here on the output, which will just tell us, is it a dog, or is it a car, or is it a cat, or what thing do we see in the image. It does not tell us anything about where in the image, how big this cat is, how small it is, or anything. It simply just tells us, given an image, what do I like, one thing I see in the image. So let's try to look at what possibilities there are to go beyond simple image classification. So here we have an image of a car. So with this here, we might be able to do image classification and classify this image as a car. Then we can do classification with localization. And finally, we can do what is known as detection. And the difference here is that single objects, that's what we're looking at for image classification and image localization. And multiple objects, that's what we're looking for in image detection. So one method here, the naive method here that one might think of, is a sliding window approach. So instead of putting in our full image, we just put in a smaller subset of the image. For instance, we crop out this quadrant first, then we slide over the window, then we classify this quadrant, then this quadrant, and all over. We might vary this window a bit to make it bigger or smaller, and hopefully over time then we'll figure out, okay, that there is a car here in the image. So this here can also be done a bit simpler, at least for localization. So instead of only predicting the class that we're seeing in the image, we could also predict the bounding box. And this could be done by, for instance, having, beside providing the image in this case here, then we'll also provide the center of this box, the x and y coordinates, and then we'll provide also the width and the height of the box where our object is located. So obviously you also need this here when you're training the system. So you need to, not only when creating your training data set, then you do not only need to specify that there's a car in the image, you also need to specify where is the car using this x, y coordinates and the width and the height of your bounding box. So instead of having a label output saying car or not car or cat or something, then you might have the output looking something like this here, where the top here, PC, is the probability of a class existing. So in this case here, we have, 3 different classes plus background. So for instance, in the case where we do not have any of the items, like no car, no motorcycle, no pedestrian, then we'll put a 0 probability in this P of class. And then it doesn't really matter what we set the rest of the stuff to in our output. But in the case, for instance, that we have a car, in the case as in the top middle picture here, then we'll set the probability here to 1. Then we'll specify where this is located in the image, the x and y coordinates, and then we'll specify here in the button that no, it's not a pedestrian, yes, it's a car, no, it's not a motorcycle that we are having in this box here. But instead of having this object localization, what is more often used is detection. So instead of only detecting one single object in a photo, we would like to find all the different objects that we are able to classify. And as we already saw, the naive approach will be something like the sliding window approach, where you would have this window that you slide over your full image. But for instance, it might not be that interesting what is in the lower quadrant here. And then we have used a lot of energy for our neural network to try to classify what is the item in our lower quadrant of this center image. So the idea behind region CNN or RCNN is to bypass the problem of selecting a large number of regions. So the idea is to segment the image into regions, which we use as CNN to classify. So first there's some other pre-processing method that have to be performed to find these regions. So by inputting some image, then we extract a lot of regions, proposal regions. And in the paper from 2013, they mentioned that they use around 2,000 different regions. Then each of these regions, they crop to a standardized size, compute the CNN features, and then finally there is some classification going on the output. In fact, here in the paper from 2013, they're using a support vector machine in the output to do the classification. So the CNN is just used to extract the features from this image, which is again an extraction from this region proposal. So some of the problems with region CNN or RCNN is that it takes a long time to train the network, where 2,000 region proposals have to be classified. So it's not a single pass through of the network. You have to pass the image, have to be passed through in parts of 2,000s. So you're passing through 2,000 small regions of the image through a classifier. So it's definitely not usable for real-time applications. And also there's no learning happening in the region detection. So we might benefit from some learning instead of where we then get to know where interesting regions might be. So before looking into the details of how we can speed up and improve on this region CNN network, then we need to understand how fully connected layers in a network, they can be turned into convolutional layers, such that we have what is known as a fully convolutional neural network, so that all layers in the network, they are fully convolutional. So here we have a 14 by 14 by 3. There is some convolution 5 times 5, max pooling, and then we have these fully connected layers. So here in the lower, we have exactly the same three, the input image, and then convolution, pooling. And now we can, instead of the fully connected, we can in fact make use of a 5 by 5 convolution here. Then we'll end up with exactly the same number of parameters and the size of the output here. Then in the next layer, we can then do 1 by 1 convolution and just keep this dimensionality of 400. And finally, we can then also do a 1 by 1 convolution and have a smaller number in the feature maps. So now we take this idea of the fully convolutional neural networks, where we have convolutions end-to-end in our neural network, and turn this into what is known as the convolutional sliding window. So let's look here in the top, where we have a 14 by 14 by 3 image. We do some convolution, and eventually we end up with a 1 by 1 by 4 output, meaning that we are classifying this image into one of 4 classes. So we get a probability for each of these 4 classes. Let's have a look at if the image was slightly bigger. And now we have a sliding window of 14 by 14, which we slide over these 4 placements. So after the 5 by 5, in fact, the receptive field, so we're just highlighting the blue area here, has in fact direct connection to the blue area in the input, our image here of 16 by 16. After we do max pooling, it still has the receptive field is still this upper left quadrant. And if we do, just as in the top row, a few more convolutions, then we end up that the output is now 2 by 2 by 4, where we have the upper left item here. Well, it also has 4 items, so now we have a classification for the upper left area of our input image, and the lower, so classification of the green area here of the input. So in this way here, we in fact avoid having to pass through the network 4 times. We can just do this in one go by this convolutional sliding window setup. Now we can look at what if we increase our image. So usually you would have a bit more than 16 by 16 images. Maybe you have 28 by 28. Then it will look something like this here, where this single output would then be the classification of the upper left quadrant. So the improvement of RCNN is what is known as fast RCNN, and the fast here is as the convolution operation is implementing the sliding window, as we just saw on the last slide, to classify all the proposed regions at once. So instead of having all of these 2,000 small regions that we had to pass through the network, then we just simply do this at once. But it is this fast RCNN still is quite slow to propose different regions to put into the network. This is now where faster CNN comes into the picture, which identified proposal regions from a convolutional neural network. So now we're closer to having something fully convolutional from end to end. So instead of identifying interesting areas of our image with some other approach, now we also have a convolutional neural network to find these areas of interest for us. And we also see here on the right just the test time speed to do the predictions of an image. So we have an RCNN which took 49 seconds, I think this here is it, and fast RCNN took 2.3 seconds, and faster RCNN now takes 0.2 seconds. So there's still some problems with all the RCNN variants, as all of them, they use regions to localize the objects within the image. So instead, the people behind You Only Look Once, also short for YOLO, they look at the complete image and divide this into a grid. And this makes it much faster than the RCNN, though the first version of YOLO had some problems with small objects within the image that it couldn't detect that well. So we see here an example of how it works, that it puts on this grid onto the image. Then it has a lot of bounding boxes with confidence, and then both this class probability and these bounding boxes then combines to the final detection. So YOLO version 1 was published in 2015. After that, there was 2 other papers by the same authors, YOLO 2 and YOLO 3, which both significantly increase the speed of the system, plus it also introduces a more dense grid at the same time, which makes it possible to detect smaller objects. And in fact, YOLO is still one of the fastest and most precise methods to do object detection. So this year, the YOLO version 4 was just introduced, which also has the title Optimal Speed and Accuracy of Object Detection. So interesting enough is that the same authors were on YOLO 1, 2, and 3, and now here in version 4, it is some other authors that have carried on the name. So on the MS Coco dataset, which is an extension, I would say, a newer version instead of ImageNet, which also looks at object detection and also the timing for this object detection, it outperforms all other methods. And I also had a look at papers with code, where you could do some comparison what papers performs or what methods performs how well on the Coco dataset. And there, if we look on the accuracy point of view, then YOLO v4 is not the most accurate. There is something else called EfficientNet. But then if we look at the real-time capabilities of YOLO version 4, it is by far the fastest type of object detection network out there at the moment. In summary, fully connected networks, they are not feasible to use on images, as it would introduce way too many million parameters to train on. So instead, we should be using convolutional layers to detect features in images. And the idea is that all objects that we're interested in, they are built up from simple features, which we can then extract using these convolutional layers. Convolutional neural networks, they're also robust against object transformations. And on a side note, as I explained in the lecture here, convolutions in neural networks is what is known from the literature as cross-correlation. By adding these convolutional layers to our network, then we'll add a few additional hyperparameters in our system, namely the kernel size, stride, padding of these kernels or filters. Then on a side note, we should use existing architectures with modifications for similar tasks instead of coming up with our own new neural network architecture. And if possible, then we should use pre-trained networks and transfer learning, especially when data is sparse. And finally, then just credits to the books, the material that was used to create this lecture here. So the books, other online courses, and some GitHub repositories.